Okay, so with respect to the color of the complex, which was not able to explain by the VPT, crystal field theory came across with that. He says that basically if a complex has to be colored, there are mainly three reasons. One is the presence of the unpaired electrons. Presence of the unpaired electrons. The second one, he says that the presence of the vacant d orbitals. Vacant d orbitals. And the third most important thing, he says that the presence of degenerate orbitals, that is the orbitals having the same energy. These are the main three reasons which are promoting the color to the complex. For example, if a mere explanation, if we say, remember, why we are saying what is the major explanation for the color of the complex is. So what happens if I consider an electron in my T2G set and there is an EG set, okay? So what this electron will try to do, as when it absorbs the energy, it will get excited to the higher energy. And when it gets excited to the higher energy, a part of the energy will be utilized for excitation and remaining part will be liberated out. And if that liberated energy is having a wavelength with respect to the visible region, the complex will be observed as a colorful complex. That is the main reason why does a complex appear as a color. But the major important thing we have to remember that complexes are colored only if there the ligands are present. Or it's why? Because in the absence of ligands, we are writing all the 5 orbitals in the one state. That is, they are all degenerate. No splitting has taken place, so no transition takes place. So only in the presence of the ligands they appear as color. For example, if I say as TiH2O 6 times of 3 plus, of course this is having a color of violet. Why? Because here 6 water molecules acting as a ligands. But in case if I am going to heat it strongly, the same complex becomes colorless. Why? Because all the 6 water molecules are getting evaporated or they are going kicked out of this complex, only leaving back your central metal atom or the ion. So that will result in the colorless of the compound. Similarly, if I go with my copper sulfate pentahydrate, we all know that it is having what color? Blue color complex or blue color salt. But when I am going to heat it very strongly, it becomes colorless and is also called as an anhydrous copper sulfate. Because what is happening over here, if you just see, it is having CuH2O 4 times, your SO4 and a H2O. This is our complex part. You could observe that it is having the water molecules as a ligands. And when you are heating it very strongly, what happens? These molecules will be kicked out and only copper will be remained. There will be no transition of the electrons takes place. This is the first important thing we have to note, that only in the presence of the ligands complexes are colored. The second most noteworthy point is with respect to the d orbital configuration of your central metal atom or the ion. That is, if you are having your D0 or D10 configuration with respect to the central metal atom or the ion, no color is observed because there is no transition taking place in D0 because there is no d electrons, and in D10 all the electrons are paired up. That is the reason no transition takes place. So central metal atom or the ion, if it is having a D0 or D10 configuration, even in the presence of the ligands, they are assumed to be colorless. For example, if I choose the same example, Ti3 plus, so this is having the configuration of argon 3d1. That was the reason that it is having, in the presence of the 6 water molecules, it is violet in color. But if I choose as Ti4 plus, what happens? Argon 3d0. Even though it is having the 6 water molecules, but the d orbital is not having any electrons for the transition to occur, and this will lead to the colorless. So these are the major important things we have to deal that why certain complexes are colored and why certain complexes are not colored, and what are the criteria for the complexes to be colored. So in my next session, we are going to deal with the isomerism in the complexes.